Okay, hello everyone. It's really a pleasure to be here amongst all the video understanding people. And today I'll talk about our work on video understanding that we carry out in Hacettepe University Computer Vision Lab. So as we all have been talking about today, there have been significant progress in video understanding in the recent years. Just to name a few very powerful models, we have I3D, non-local neural networks, video action transformers, and all the models that our wonderful speakers told us about today. And also there have been very comprehensive data sets, AVA data set for action localization and recognition, how to 100 million data sets for how to videos have been proposed and introduced to our domain. So actually today I will talk about some subdomains related to video understanding, and my talk will be consisting about 3 parts, and in this talk towards the end I will reduce the amount of supervision, and basically I will try to pinpoint some directions to explore regarding these domains. So the first part of my talk will be about collective activity recognition. So collective activity recognition, as you know, is basically defined as the recognition of the activities of groups of people that are done collectively. So basically, this is a relatively less studied topic of activity recognition. And basically, when you look at this domain, the data sets, the benchmark data sets are really limited. So basically, there are 3 data sets. The second one is a version of the first one, the collective activity data set and the volleyball data set. And collective activity data set has a relatively smaller number of videos which are paused videos, and volleyball data set has a larger number of videos, but the domain is only limited to volleyball. So in order to address this problem, what we did is to collect a data set which we call collective sports data set. Why do we go to the sports domain? Because it is easier to find collective activities inside sports domain. It's not really easy to locate the collective activities. So in this domain, for example, we can have a gathering, dismissal, passing, attacking, and so on. These are the kinds of collective activities. And this is also a multitask data set in the sense that we can also have the sports category recognition because we have collected these activities from different sports categories. So basically in this data set there are 5 collective acts. I know that this is a very small number, but it's really hard. I mean, if any one of you has any ideas, that would be more than welcome about the possible collective activities. So there are 11 categories. The number of videos are around 2000K, and the number of frames are around 160K. The more challenging part is the viewpoint can change, and the camera movement is non-stationary. So all these sequences are collected from YouTube. So basically, when we run a benchmark evaluation over this data set using the standard action recognition techniques in a single task fashion, we get the following accuracies in the standard supervised evaluation. And when we train this in a multitask fashion, as you can see, the accuracies are increasing. So these are the, for example, the temporal stream of the 2-stream network, and this is the 2-stream network itself. So as you can see, the numbers are actually somewhat higher, and especially for the sports case, we are almost certain which sport is the video belongs to. So this gave us the raise of question. So is the collective activity recognition influenced by the availability of context? So in order to see whether we are being affected from the context, what we did is we had another set of evaluation protocol, which we call unseen sports evaluation, where we make the sports in the training and test sets mutually exclusive. We have a set of sports in the training set, and we test on the remaining sports in the test. So for gathering activity, you train over a number of sports classes, and you test for the gathering activity, for example, in the left out sports class, such as water polo. And when you do this, you see a significant performance drop in the overall accuracy, and this suggests that collective activity recognition in this in the sense can be really affected from the overall context. So we have to be careful about when the model is really learning the essence of the activities, or it is learning the context. Okay, so this was the first part, and the second part of my talk, I will jump into another domain, which is the face recognition in the wildest domain. So by wildest, I mean, we are all familiar with wild, but by wildest, we mean the videos in the violent scenes. So actually, face recognition is a largely solved problem in controlled scenarios, over 95% accuracies. However, there may be cases, especially in the surveillance cases, where policeman wants to identify some criminals, and the footage they have is the violent footage. So in that sense, people in criminal activity expose a diverse set of expressions, and there are lots of blur and different artifacts. So another challenge in this domain is that the people in criminal the people who has done the criminal activity may not necessarily have prior criminal records. So they may only have passport or Facebook-like type photos. So this is like a domain transfer problem. So in order to facilitate research in this direction, we have collected the wildest faces data set. And while we are doing this, we collected violent video scenes from movies. I mean, the students made searches like car chase, fist fights, gunfights, and heated arguments from the Hollywood movies. And we also gathered the clean images that are already readily available. We did this for 64 actors, and we had more than 2,000 shots and 8,000 images. So these are the clean images, these are the violent scene shots. And as I said, some criminals may not have prior violent footage, so this is a partial supervised setup. Our evaluation setup is trying to depict this scenario. So during training, we have clean images of all the people. So we have access to the clean images of all the people, but some of them have prior violent footage. And in the test, we have the videos of all classes, seen or unseen. So the dataset looks like this. We have these clean photos, and we will try to recognize the violent faces in these video shots. So actually, as I said, this is a partial supervised domain transfer problem. We have firstly, we have a source domain classifier, which is defined over the images. And we should have a target domain classifier. And what we do is we do a temporal adaptation followed by a classifier transfer to handle this case. So for classifier transfer, we can basically very simply use the fully connected classifier transfer layer. But when we tried this, we saw that there are many parameters to estimate, so it doesn't work well. So we tried simplified affine classifier transfer, and also we can have stacked versions of these, and also a version where the residual where there's a residual connection. So what we call is the residual stacked affine classifier transfer. And for temporal adaptation, in our video representation, the simplest thing that we can think of is average pooling, but this is not, of course, a very good idea. Why? Because the video sequences are very noisy. It's not an intelligent thing to do, to rely on all the frames. Here we propose to use a better alternative, which we call attentive temporal pooling, which consists of an attention layer that attends over the important parts of the sequence and then does a temporal pooling over with those attentive weights. Okay, so for the classifier transfer, we compared with some domain adaptation techniques, and we see that the residual stacked affine classifier transfer worked the best, but still the accuracies are not that high. And also for temporal adaptation, we have compared it to a gun-based version approach, and also self-attention approach, and attentive temporal working worked slightly better than those. However, again, the accuracies are very low, so there's a large room of improvement here. Okay, so I have 3 minutes left. So the third part of my presentation is about sign language recognition. As I said, I will reduce the amount of supervision. So in sign language recognition, most of the approaches require a large amount of annotated data to recognize predefined sign classes. So there are two problems here. One is the need for excessive manual annotation, as we all know. And the second problem is, what if we want to recognize other signs? So you can ask why this may be an issue. Actually, this may be an issue because languages are constantly growing. If you check the website of the Oxford English Dictionary, you can see that thousands of new words are added to the dictionary every year, and this is the same for sign languages. So in order to deal with this problem, we propose to use sign language recognition in a zero-shot setting. And as in all zero-shot settings, we have seen classes and unseen classes, but we have to use some auxiliary information to infer the unseen classes. We can use attributes, but attributes needs manual annotation as well, so they may not be optimal. So instead, we think we can use the textual descriptions of signs. And for this purpose, this is the videos from the ASL-VD dataset that has been collected by Boston University a while ago. And we have taken the videos from this dataset and augmented it with the textual descriptions of the signs taken from the dictionary, sign language dictionary. So these descriptions, textual descriptions, comes from the sign language dictionary. Okay, so the ZSLR model that we propose here is a model that looks like this. We have the video representation, two stream again, one working on the whole frames, the second one works on the hands, and we extract the i3D features from them. We need a longer term modeling, and we use the bidirectional LSTM for this purpose here. And the textual embedding, we have to have an embedding for the text. For this purpose, we use the BERT embeddings, and at the end, at the ZSL components, we learn a compatibility function between these video embeddings and the text embeddings. And when we look at the textual embeddings more closely, so this is the TSNE representation for the textual embeddings. You see the training data classes, test and validation data classes. When we look at the closer points, we can see that they are really indeed closer in nature. So for example, these two classes, one from the training set, one from the test set, friend and hamburger classes, as you can see, they are very similar to each other. So this shows us that the text embeddings are meaningful in this case. Okay, so I'm going to wrap up. So in our experimental settings, we had for training for 170, for validation 30, and for test 50 classes. We have compared with some zero-shot learning methods, and we have compared some of the different temporal modeling methods. Here, this is really a challenging problem. The top one accuracies are quite low, and there's a room for improvements here. You see an example outputs here. Okay, so based on the overall experience over these domains, what directions can we explore? I think we need certain methodologies and test beds about the activity recognition and video understanding in general to understand whether we need to use context or we need to unlink from context. So we need that kind of methodologies. We have to look for the problems. We have to look at the diverse domains and how to transfer knowledge between those diverse domains. And we can use this partially supervised techniques or unsupervised techniques. And also, we have to find ways to deal with the excessive need for annotation and ever-growing dictionaries such as few-shot, zero-shot learning, or self-supervision. Okay, thank you very much.